Yeah, thank you, Patrick. It's my pleasure to be here. I'm going to talk a little bit less maybe about the interface side of it, since the radar itself is the sensor. We don't really have a separation between the sensor and the interface. My goal is to share with you a bit of what has happened in millimeter wave radar, specifically on automotive, and then pivot to new applications for radar, and specifically what is needed to enable those applications, which is more architectural and high-level signal processing. So I'll begin with actually just basically this is the recent history of radar. This basically spans the entire time of the TI radar product development, roughly over the last 10 plus years. And when we look back, so radar, automotive radar is today at between 76 to 81 gigahertz. The actual development of this started about 50 years ago with initial demonstrations that were massive size on, like, say, the front of a Mercedes. And then there's been a commercial adoptions roughly for the last 20 years. And at the time when we started, it was still on very high-end vehicles, things that I wasn't able to purchase. And now every rental car I get is like at 2 to 5 radar sensors, which is great to see. And this has really been enabled primarily through significant convergence of technology. Everything has moved into CMOS over the last 10 years. We've also seen the chips have gone from integrating the front ends directly with everything, and now basically this generation of radar sensors is all essentially a radar on a chip for most of the deployments around a vehicle. And what has happened with the transition to CMOS is obviously we've gotten things smaller and generally lower power and lower cost. But it's also significantly improved the performance. We've gotten to have larger flexibility in the waveforms that you're able to create that allows you to do more sophisticated ability to do a higher angular resolution, as well as to do interference mitigation, bring in new features, as well as more diagnostic mechanisms within the radar itself to enable higher levels of functional safety. Radar is one of the safeties, is part of the safety systems in a vehicle, and it itself cannot fail. So, what does the radar look like today? So this is an example of a high-end radar on a chip. And it is essentially, at its heart, on the RF side, there is a 20 gigahertz synthesizer here that is doing FMCW modulation. I'll talk about this in a little bit, but it's basically a modulated synthesizer that's generating frequency ramps. It is distributed to multiple transmitters, multiple receivers, and then these all include digitization. And all of this does edge-based signal processing using a combination of a hardware accelerator to do low-level signal processing, primarily FFTs, then a DSP to do higher layer signal processing, and then a safety MCU to be able to do the final application level decisions, communications, and maintain the functional safety of the overall system. And really, over the last 10 years, what has happened is that the power per channel, so the power per RF channel, either a receive channel or a transmit channel, has reduced between 2 and 4x. This allows you to basically make the radar sensors smaller because they're thermally limited, or to increase the number of channels within that. In addition, basically the IF bandwidth, so the speed of the ADC, has increased roughly 2 to 4x. And this allows you to do faster radar processing in chirps and allows you to handle scenes with wider dynamic ranges of velocities. So the original radar sensors were actually on a highway, and you'd think that's very high speed, but highways are very simple because everybody's going at the same speed. When you're in an urban scenario, you can be in a situation where you have a pedestrian or vulnerable road user that's traveling at very slow speeds and a car coming at very high speeds. You need to be able to make instant decisions, so you need to be able to handle very wide ranges of velocities in that. And then also, we've also been able to double the number of virtual channels, which is the product of the number of receivers and transmitters. And this improves our angular resolution. So what are the applications? So basically in automotive radar, today, ADAS, or Advanced Driver Assistance Systems, these are widely deployed. Very few car manufacturers advertise radar. Radar still has a sort of a bad impression because it starts with the same same letters as radiation. But automatic cruise control, emergency autonomous braking, blind spot detection and lane change assist for side-looking radar, and cross-traffic alert, either forward when you're entering an intersection or backwards when you're pulling out from your parking spot, are widely deployed features that you'll read about. And then over time, we've had an increasing field of view, increasing range, and more radars around a vehicle. There's also new applications that are sort of bridging this motivation to the beyond ADAS world, where, for instance, you can now have kick-to-open sensors on your trunk, which I'll show a little bit later, as well as in-cabin radars are now being deployed to detect the presence of a child after the parent has walked away from the vehicle and to notify the parent, and this is to prevent heat stroke on a hot day. It might not happen in San Diego, but in Texas, that's very common, or it's very common to have that be hot enough in the summer. So I'm going to begin the general sense of the talk is to look first at some radar fundamentals. I would assume most of you are not radar people, so I'll give some background on radar itself, what we measure, what are the characteristics. Then talk about a few applications, starting with building automation, which is a people detection application, people detection and classification, go into human-machine interfaces, and then end the talk with imaging, which is sort of the most challenging portion of radar, building high angular resolution sensors. Okay, so what does the radar waveform do? So at the heart, a radar sends an electromagnetic signal and measures the response. And in particular, the radar systems that are widely deployed now use something called frequency modulated continuous wave radar. So in this case, the transmitter is outputting a constant envelope signal, and the frequency of that signal is ramped linearly over time in this repeated sawtooth fashion. This goes out, it will reflect off of objects in the scene and be reflected and come back to the radar receiver. And you can actually see the receive waveform. There's two specific shifts here. So it's shifted to the right, and this is due to the round trip time of flight to the object. It's also shifted vertically, and this is the Doppler effect, or the Doppler shift. So if the radar is approaching the object, that means the reflected signal will come back at a higher frequency than you sent it. It's also the same thing as a blue shift in radio astronomy. And if the object is moving away from you, it'll come back at a slightly lower frequency. So on the radar receiver, there's a mixer that will actually just mix the transmit and the receive waveform. And the mixer, for practical purposes, is a frequency subtractor. And you can see here that you get a constant frequency in this region. So what you get out in the IF baseband of a radar receiver is you will see targets whose frequency is proportional to the range of the object. In addition, we're doing this many times. So we're sending out many of these chirps. And if you actually look from chirp to chirp, if an object is moving with respect to the radar sensor, the phase of each of these targets will shift by a small amount from chirp to chirp. And if you can measure that phase progression from chirp to chirp, you're able to get the Doppler or the radial velocity to that object. So the basic radar signal processing for FMCW is you get this receive waveform, you do a two-dimensional FFT in the digital baseband, and now you are able to simultaneously recover range and Doppler. So the third thing that radar can measure is the angle of arrival. So the angle of arrival requires multiple antennas. It can be done on the transmitter, it can be done on the receive side. Here I'm just showing you the receive example, which I think is more intuitive. So let's say you have the received wavefront coming from the right side here, and you'll see that it hits channel 4 slightly before channel 3 and so forth. And that means that slight early arrival will lead to a time difference of arrival between these two, which actually ends up being you can measure as a phase progression across the receive channels. And you can therefore, if you can estimate that phase progression, you're able to understand the angle of arrival. So the first thing to notice is that, the phase progression really can't go beyond plus or minus pi, otherwise you can't tell which direction it's coming from. So that means that the antennas would have to be spaced at half of a wavelength in order to have an unambiguous field of view of half of a hemisphere. And it turns out that if you want to be able to separate out multiple received objects that are coming in at different angles, the angular resolution, which is how closely these objects can be, the angles of these reflections, is inversely proportional to the aperture size of the antenna, of the overall antenna. And as I said, the aperture size is based off of the antenna spacing and the number of elements, and the antenna spacing is fixed. So you're really talking about that the angular resolution is inversely proportional to the number of antennas. So radar is extremely good at distance and velocity measurements. However, it's pretty poor in terms of angular resolution. So this flagship product, which is sort of the state of the art for automotive radar sensors, it has a total of 16 virtual antennas. So it's the equivalent of a 16 pixel camera. So that's like when you're in a single range Doppler band, that's all you have is 16 pixels. So if you're thinking about this from the camera world, which are, you can get megapixel cameras for like $1 today easily inside an automobile. This is a totally different type of information you're going to extract from the sensor with this limited angular resolution. And some key characteristics here are really the motivation to higher frequencies. Radar started out, sub 1 gigahertz and sort of then migrated to 10 gigahertz, 24 gigahertz, and now 77. And this is all driven by better resolution, so being able to separate out objects more effectively. And this comes because the range resolution is inversely proportional to bandwidth. You get more bandwidth at higher frequencies. The velocity resolution is inversely proportional to wavelength, so smaller wavelengths, better velocity resolution. And then angular resolution, as I just showed, is proportional to the wavelength over the aperture size. So for a fixed dimension, you can get better angular resolution at higher frequencies. So that is shifted now so that, at least for the automotive space, everything is about 77 gigahertz. And in research, people are talking about even higher frequencies. And I'm skeptical about automotive, but for other applications, I think it'll happen. The last thing that's significant about a radar, at least that I'll talk about here, is how far can you sense. So a lot of math here. I'm not going to go over it in detail, but the maximum distance is a factor of many things. So sigma, which is the object reflectivity, it's a heuristic of sort of the object reflectivity. It can vary, several orders of magnitude in automotive and another couple of orders of magnitude when you're detecting people and their motions. And then the main factors for what limits range are the technology, the available output power and noise figure that you can meet, the frequency, you get lower range at higher frequencies, and then the field of view. So the antenna gains are inversely proportional to the field of view. So if you want to see a very wide field of view, you're going to be talking about lower distance. The other thing is if you're coming from the wireless world, you can see that the exponent here is 1/4. So the path loss drops off at 40 dB per decade. If this is compared to a line of sight communication link, that's 20 dB per decade. So for the same RF parameters, the radar will be able to observe objects at shorter distances than you'll be able to communicate with them. So just something, in terms of how far a radar can sense. Okay, so ADAS radars. So radar is essentially at this point, it's the preferred sensor on a vehicle for poor visibility conditions. So rain, fog, snow, bright sunlight, darkness. Radar is essentially mostly insensitive to those. It primarily detects moving objects around a vehicle. So it was originally deployed in highways. We were only detecting the vehicles that are moving on the road. There's been some well-advertised crashes of vehicles where radar sensors didn't see static objects. And it's also the preferred sensing platform for long distances. When we compare it to cameras or LiDAR or ultrasound, radar has the longest sensing distance, at this point around 270 meters in a vehicle. Automotive sensors are designed to be thermally limited, so they're passively cooled, so it's about 5 watts for a corner radar, and then about 20 watts for a slightly larger front-looking radar. This is a totally different class of radar sensors than most of the things that you're going to talk about today, which are more on the, let's say, microwatt to milliwatt level. And radars, I'll repeat again, is that radars give you rich depth and velocity information and very limited angular resolution. So then the question is, what can we do with these? What can we do with a millimeter wave sensor beyond ADAS? So the first thing is looking at what applications are well fitted for this. And because radar does very well detecting motion and classifying motion, so it's the applications that are built around motion detection and motion-based classification are the most natural fit. And I'll show a couple of examples there. You need to use higher layer information to really get data from the radar. I'll show you some point clouds in the videos, but you can't, when you're looking at this point clouds, you really can't tell what an object is or what it's doing. And especially, very few applications really can take a 5 or 20 watt box and do a lot with it. And so you need to really look at architectural and system changes to go from, battery or car engine powered radars to something that could be battery powered. And then finally, as we look at new uses for radars, you get into increasingly cluttered environments, and in particular, indoor environments are highly cluttered, where clutter is anything that we don't want to sense. And so there's a bunch of static objects that are everywhere, and it becomes problematic in terms of overall scene handling. So I'll start with sort of how radar sensors have moved, the actual radar architecture has moved from the automotive 77 gigahertz radar to an industrial sensor. So the automotive band is restricted by regulations around the world. Different countries are slightly varying, but roughly 76 to 81 gigahertz. If we want to do anything outside of ADAS, it's got to be a different frequency band. And the widest frequency band that's available, at least in the US and Europe, is the 57 to 64 gigahertz band. And so the first generation of radar sensors in this band for industrial applications simply duplicated the automotive radar architecture and just did a frequency translation. So that can be done, as I showed earlier in the block diagram. The fundamental frequency was actually at 1/4 of the RF frequency, so 20 gigahertz. That was generating all the local oscillator waveforms. So you just replace a frequency quadrupler with a frequency tripler. And now we are able to have a sensor that's centered around 60 gigahertz. In addition, as we look at the front end chains on the power, let's say the PA or the LNA. So for millimeter wave, these are basically just cascades of common source or differential common source amplifiers with transformer-based interstage matching networks. And architecturally, you basically want to, if we're just doing a simple frequency translation, it comes down to really all you're doing is scaling the interstage matching networks. So redesign your transformer, redesign your capacitor, and suddenly you can go from 77 to 60 gigahertz in the same area and roughly the same power. As you're going down in frequency, things are easier. We're very, everything at millimeter wave is very gain starved in modern technologies. At 60 gigahertz, you would get more available gain. On the flip side, the absolute bandwidth at 60 gigahertz is higher than at 77 gigahertz, and the relative bandwidth is even that much higher. And this means that you actually end up getting about the same gain per stage because you're trading off higher available gain and trying to operate over a wider bandwidth. And the last thing as we get into new applications is we want to be able to miniaturize this. So this goes down to getting the antennas to be as small as possible. And now antennas are basically chip scale. So everything can be done. The entire radar sensor can go from a radar on a chip for all the electronics and now actually integrate the interface with free space for the electromagnetic waves. And this is done as shown here. This is basically it's a FCCSP package with an undermount configuration. So the die is on the bottom side of the package. The antennas are formed in the top layer of the package with a ground plane on the third layer up. And then between the antennas, you can see a whole bunch of textured elements in this view. These are an electromagnetic band gap, which is basically a metamaterial that is resonant at 60 gigahertz and prevents propagation of waves between the different antenna elements. And this gives you a cleaner radiation pattern and improves the transmit to receive isolation. Now, the last thing is going from watt level to milliwatt level. And this requires a bit more optimization, as well as taking care of some of the careabouts of the applications. So in particular, when we look at going from detecting cars moving on the Autobahn to people moving in buildings, it's much shorter range, and people move a lot slower. So we can take advantage of that and sort of re-optimize the radar sensor around that. So moving indoors, moving slower speeds, we can reduce the IF bandwidth. We don't have to handle as wide of a dynamic range of velocities. So this will help reduce the power dissipation, go from a complex to a real baseband. This does have some sacrifice of SNR, as well as interference resilience, but it's a good trade-off if you're looking to optimize power. On the transmit side, we don't have to put as much power into the scene. We're not seeing as far. So we can go from a four-way, which is basically 4 parallel stages of the PA that are feeding a single antenna, to a 2-way combined PA. Theoretically, that should reduce the power by 3 dB. In practice, the power combiners themselves are lossier as you get to larger power combining. So this actually ends up only being about a 1.5 dB reduction in output power. We also change our clocking architecture to reduce, it's a cascade of an integer NPLL and a modulated FMCW PLL. We can reduce the frequency of the integer NPLL, trading off some phase noise, once again for power dissipation. And then finally, building a radar sensor digital hardware that is able to wake up, take a measurement, make an instantaneous decision, and then go back to a deep sleep mode with comprehensive power management so that you're really being responsive to the scene around you and getting an average power that is approaching about 1 milliwatt. So about 3 orders of magnitude lower power than the first generation of sensors. All right, so what do we do with this? So I'm going to show a couple of examples of applications, and starting with a building automation application, which is intended around detecting people and how do we do this inside an indoor environment. So The basic application here is people counting. We want to be able to detect and track people indoors. It could also be outdoors. Indoors is a bit more challenging. And you can do this. This could be, optimizing your heating and air conditioning, adjusting the amount of airflow that comes from outside the building based off of the number of people there. Or the latest thing that people are looking at is trying to direct air conditioning either to people or away from people based off of their preferences. You can also optimize lighting in a building. It can be used for building security. And then it can also be used as an emergency response. So if there's smoke in a building, you wanted to direct first responders to the room where the people are, you need a sensor that can still sense in the presence of smoke, which radar can do. When we look at, just as an example of this picture, this is our team that developed this in the office. Indoor environments are heavily cluttered. Every one of these surfaces reflects. You can see metal table legs, metal cubicle walls. There's windows. All these reflect very nicely. So you have a lot of clutter. You can also see that these people are sitting quite close to each other, so the reflections and the point clouds will be overlapping, so it's hard to distinguish them. So the approach that we've taken is, first of all, ignore everything that's not moving. So the first step is we directly extract the velocity information, so start by filtering out anything that's static. Then do a higher level localization, a group tracker that will separate out the points in the scene based off of the history of the objects in the scene. So this is a combination of a clustering and a tracking step that will basically is cognizant of the fact that a person doesn't suddenly appear, suddenly split, or suddenly disappear. So you can look at the history of what's in the scene to make sense out of it. And then finally, even though we're ignoring static objects, there's a lot of things that move that are not human inside an indoor environment. This could be a pet, it could be a fan, it could be the plant leaves blowing in the wind, blowing in the air conditioning. And you don't want to, let's say in a first responder scenario, you don't want to direct a first responder to a room where all that's in there is drapes that happen to be blowing because there's smoke going by. That would be a big problem. So how do we do this? And this comes down to all basically signal processing. So at the lowest level, the radar sensor is sending out just raw ADC bits. I mentioned earlier that there's a series of FFTs, and these can be used to extract the range, the radial velocity, and the angle. And then at the end of that step, this creates those FFTs will create a radar data cube, which is a matrix, a three-dimensional matrix with range, angle, and velocity on the three axes. Then there's a detection step, which will look for local maxima in that. And in this case, you can use a CFAR detector, but effectively that will create a point cloud. So now we have all these local maxima within this data cube. We can get out tens to hundreds of points. And we want to figure out, well, what are these points are? So a person, if you have a radar sensor that's got maybe 5 centimeters of range resolution, we are much larger than 5 centimeters. So a person might give you tens of points. So the idea is that we want to go through a step that will partition the scene to figure out how those points map to objects, and then track those objects over time, and then finally be able to classify them. So I'll start with the localization step, and this is combining that scene partitioning and the classification into one combined algorithm. So I'll go through the group tracker in a few slides, but assume for now that you've already seen two objects are in the scene from the previous frame. So this is done on a frame by frame basis. So there's two objects, and those objects, the output of the tracker is an object state, which includes its position, its dispersion or something equivalent to size, as well as its heading, so its velocity vector. So the first step is, okay, from the previous frame, I knew where these objects were here. I knew what their vector was, what their velocity was, so I just, update and predict where they will be in this new frame. I'm also showing the instantaneous point cloud returns from the detection step on the current frame. So the next step is we knew where the objects are. We also know a relative sense of their size. So we will attempt to associate the new points with these objects. So, it's pretty easy here just looking that some of the points, when we try to gate these, you can see some of the points are obviously in only one object. So U8, U9, this is only going to be in the green object. U7, U3 here, these will only be in the blue object. So some points are easy. But in reality, because you have poor angular resolution and people can stand pretty close to each other, you'll have point clouds that are overlapping. And but by doing this together, you can still separate out the points based off of their most likely most likely object, and associate that based off of the lowest distance, so basically the lowest error in your system. And this allows you to maintain these objects as two separate states, even as they might start out far from each other, but as they're walking, they're sitting next to each other, you're able to maintain them as two separate states, knowing that people don't suddenly split or people don't suddenly disappear. You can also see that there's other points. This is U6. This would be a candidate to create a new object if you see that over a couple of frames. Once you do this, we now have an estimate of the current points for that object. You just update its state information based off of the new centroid from these points and update its velocity vector. And then this repeats frame by frame by frame. So now we have a way of taking all the points in a scene and grouping them into objects that are tracked over time. So you can see that in this video here. The raw points that are coming in, I mean, if you looked at these points, it's not really obvious that this is a person, it's just a bunch of points. We are able to robustly classify these and be able to do that even as the people get pretty close to each other. I'm not showing it here, but the next step is then, okay, well, you can see this fan this box fan on the ground. Box fans also move. Yeah, they also have a lot of radial velocity. So what do you do about that? So the next step is, okay, how do we classify these? So how do we distinguish that person from the curtain or the fan? And we want to be able to classify multiple objects in a scene at the same time, and want to be able to do this in a very resource-constrained device. These edge devices, they need to be very low cost, very low memory, and they need to have be able to do this at very low power. So the primary way that we do classification of radar is relying on sort of two basic things, which is the microdoppler and the microrange. So microdoppler is the distribution of velocities of an object over time, and the microrange is the distribution of the motion of the sort of the macro motion of the object over time. And be able to calculate these and use this to feed a classifier. And with this now you can, it's sort of hard to see in this image, but you can see after some time you'll label, this is a binary classifier, you'll label objects as human or non-human. And the basic way that this works is that we take these tracked objects at the output of the group tracker, we go back from the centroid of each object, we go back into the radar data cube, and we'll extract the microdoppler of that object. So this is the velocity distribution of that object over time, and also the microrange of that object. And then you can imagine thinking about this, when people are moving around, we have a torso that moves roughly at a constant velocity. As you walk, you sort of swing your arms and legs. And if you think about that, at any given time, one leg is moving back, one arm is moving a little bit backwards, slower than the torso, one arm is moving faster than the torso. So you'll see these sort of repeated patterns that are going to be two arms moving. Whereas like a box fan, it's got a lot of motion, but that motion is extremely regular. So you'll get like these very sharp lines in the microdoppler graph that are exactly sort of at the different points on the box fan. As those points scatter, you'll see very repeatable and regular patterns. Versus if you talk like a drape, drapes are very chaotic. So you'll see almost no characteristics of a motion of a drape blowing in the wind. The other thing about range is that many of these objects, most of them, when I talk about drapes, plants, box fans, they don't actually move they have motion, but they don't move. So if you look at the range history over time, you also sort of have a sense of, is this something that can move, like a person or a dog, or is it something that is just stationary but has internal motion? So once we have these microdoppler and microrange plots, we do some manual or custom feature extraction, extracting some statistics from this. This is required, rather than feeding this directly into a classifier or neural network. Given the resource constraints, it's better to do custom feature extraction, looking at sort of the distribution of the signals, the median and mean, as well as something about the entropy. And then from there, finally, we'll go into a two-layer CNN, followed by a fully connected layer with a binary classifier at the output. And with this, we're able to basically get roughly up to about 97% accuracy after about 2 to 3 seconds of observation. And for many of these objects, you can have extended time to even improve the accuracy further. Only in maybe the security application do you would want to get an earlier notification of what the object is robustly. And as I can show here, this is still done with very lightweight signal processing. So 3 milliseconds per track and only about 13 kilobytes of total memory in the final classifier. So that's one example where we're able to combine sort of Doppler information along with a custom feature extraction and machine learning to do the final classifier. The other area I'll talk about is another human-machine interface, but this is detecting gestures. So about 10 years ago, Google made this really nice, basically inspired a lot of people and demonstrated what you could do with radar-based gesture. And if you haven't seen those, I definitely encourage you to look at those videos, but they were basically trying to create a human-machine interface for their Google Watch. And they were able to show that they could do very fine finger gestures, relying only on the microdoppler of the hand motion going into a deep neural network. Now, what can we do with that nowadays? Or there's been a lot of research about that. So we've done some work as well, looking at sort of more coarse gestures in a couple of different applications. For the vehicle application, there's the kick to open. A lot of people already have this on their car. There's a capacitive sensor underneath the rear bumper. As you walk up to it with your grocery bags in your hand and trying to open the trunk of your minivan, you sort of swing your leg out with your smart key in your pocket. It'll identify you and the trunk will swing open. These systems have a pretty poor detection versus false alarm trade-off, and at least with my wife's car and my foot, it does not work. So I don't know if other people have better sense. Radar gives you gives you access to richer information and can provide a higher quality experience for this. I've also looked at things like dynamic hand gestures. So there are people who are doing research on static hand gestures, but given that radar can't really distinguish sort of something where your hand's not moving, we've been focusing on the dynamic hand gestures, which we think have a much higher likelihood of being able to do robust classification for this. But the architecture is actually quite similar. All these start with a presence detection mode that will operate at about 1 to 2 milliwatts, where all you're doing is sensing, is there something in my field of view? If not, I'll just go back to sleep. So take a measurement a couple times a second. As soon as you detect that there is coarse motion in your field of view, then you will wake up the sensor and go into a gesture detection mode, which is basically a combination of low-level functionality on the hardware accelerator and then high-level functionality using custom feature extraction and an artificial neural network on the microcontroller inside the system. And with this, just to show that this can do, this is the coarse hand gesture one. You can do swipes, which is, if you look at the video, he is advancing and retreating, advancing and going back on the slides, as well as these finger twirls, which combines both the microdoppler as well as angle information, because you want to be able to determine, differentiate between a clockwise and a counterclockwise motion. And if I had the volume on, this would be controlling the volume of the sensor. So these are all things that you can do with the latest round of these low power edge sensors, and getting into the high 90% of accuracy. And there's some applications of this. I mean, these are some more consumer applications, but you can imagine that this would also be useful. Let's say if you can have something where you don't have to go off and touch the screen, where it's distracting, or if you're like in a hospital where you want to have some sort of access, but you don't want to be able to have contamination of germs by actually touching a surface. The last thing I'll talk about, which is the most challenging portion, is imaging radar. And this is, can we actually use radar to detect and observe characteristics of the static environment? And this is true also for automotive, as well as for industrial or non-automotive applications. In the automotive scenario, if you actually work out sort of what you really want to detect, which is be able to safely figure out if you can drive over an object on a highway, you need about 0.3 degrees of angular resolution. And if we actually build this, I have this nice handy dandy formula. It would take a 70 by 70 centimeter box densely filled with antennas to be able to detect 0.3 degrees of angular resolution. And this, is great for a chip vendor, 122,000 antennas per car. I mean, that is tons of TI silicon. I'm very happy. Unfortunately, it would also melt because it would be, about 10 kilowatts. And nobody would put that into a vehicle. So the real challenge is, how do we get enough angle information about the scene without going to something that is either incredibly large or incredibly complex with a large number of channels that will be costly and power hungry. And the first set of these is basically just to extend the number of antennas by cascading and building larger systems. So this is our demonstrator where we take 4 transceivers. The chip here, this is the primary device. Its internal local oscillator is generating the modulated waveforms. It's distributed on the board at 20 gigahertz. All 4 chips receive those waveforms and then use that to create a larger coherent array, in this case with 16 receivers and 12 transmitters. And on this type of board, you can see that you get roughly about 1.5 degrees of angular resolution in the azimuth or horizontal direction. So this is actually a big step up from what the simple single chip radar sensors is. And we can use this to start to take a look at a bit of the static environment. So these are all non-moving scenes. And you can see, in this view in our parking lot, we can see that there's these fences with the spool of wire behind them. You can see that clearly on this. You can see the pole. We can see 2 cars that are separated just slightly above that theoretical angular resolution limit. We can also see an example where you have large objects, which are cars, and a small person in between with very clean reflections. And you can start to see characteristics about surfaces and natural elements. So the reflections from the grass look very different from the reflections from the roadbed. We can also clearly start to see the curb as well as trees. So you can start to get information on the static environment. And there are already commercial deployments of this. The first couple classes of imaging radar are on vehicles. They get roughly about 1 degree of resolution in azimuth and 2 degrees of resolution in elevation. But it's still, there's a lot of work that needs to be done to continue to push the performance there, as well as to reduce the cost and power of these boxes. So the last thing I'll talk about is what we've been doing is, looking at research, both internally and with universities, on sparse array radar, specifically to address this problem. And the idea of the sparse array is that, everything I showed previously and the derivations is assuming that we have a uniform linear array with all the antennas that are spaced at a fixed increment. But that's not really a requirement. And so the concept of a sparse array is let's spread out these antennas. Either remove antennas from the uniform linear array or take your antennas and spread them out. So for instance, with the same 12 antennas, we can see that the total aperture size here with the sparse array is much larger than the total aperture size of a uniform linear array. Now, if we just use classical algorithms to detect this, there is a trade-off. So if we look at a Bartlett beamformer or a classical beamformer, we can see that the main lobe of the sparse array is much narrower. This blue line is much narrower than the main lobe of the uniform linear array. And that's because you have a larger aperture. That main lobe corresponds to your resolution. Smaller main lobes, better resolution. The penalty is you can see the side lobes. So when you go to sparsity, you introduce a lot of side lobes into your scene. And these side lobes are actually at a high enough level that you'll basically be masking any single large object will mask out effectively everything else at that same range Doppler bin. So it becomes down to, okay, now we want to be able to, I like the fact that I can have a larger aperture or alternatively reduce the number of elements that have to connect to a chip. But how can I do this without having something where I can only detect a single object and then just a bunch of noise? So this leads to sort of the overall landscape of sparse recovery. And in this particular case, we have many things we can think about. Are we able to observe multiple observations at the scene? How many sources or targets are we trying to detect? Normally, you can only detect a number of objects that is fewer than the number of antennas you have, but that's not always that requirement is also not a hard requirement. What are we trying to obtain? Are we trying to get the best possible resolution? Are we trying to get the smallest possible size, the fewest number of elements? And with that, there's a whole range of solutions that people are looking at. So there's different array geometries. So there's all sorts of different people have come up with all different ways to create sparse arrays. There's deterministic ways that are formula-based. There's also random array topologies that go just through like an optimizer to go off and choose the array topology. And then these are combined with new algorithms that are being developed, where algorithms that are super resolution algorithms that were designed for uniform linear arrays, or new algorithms that are designed specifically for sparse array processing. And these have a couple different ways of operating, but ultimately, all of this, it's a very wide landscape, a very heavy area of research. Some of the research, we actually partner with Payapal here at UCSD on some of this in terms of sparse arrays. But the idea is to come up with array topologies, algorithms, and things that can be computationally feasible within the types of hardware that we can build, and do that in a way to meaningfully reduce the complexity of an imaging class of radar. So what can this actually do? So I'm actually going through, this is some measured results of some of these sparse array processing. So we took our Cascade EVM, which has 86 virtual elements, a dense uniform linear array of 86 elements, and then we randomly selected 16 of these elements. and then use that to image or to observe two objects that are separated by 1 degree. So first off, this 1 degree is actually smaller than the theoretical angular resolution of the dense array. And in addition, with so few elements that are selected, with the classical beamformer, traditional way of doing signal processing, you don't see anything. You basically just get a flat response out. You can't detect the objects, you can't separate out the objects, and you can't detect anything else out in the scene. But I showed, here are a couple of examples of a basis pursuit and a SPICE algorithm, both of which are able to achieve 1 degree angular resolution. They can separate out both objects, but you can see very different performances in side lobe level. And this will also translate into very different performances or very different requirements on the amount of computational complexity of these algorithms. All of these are sort of orders of magnitude more complex than the traditional signal processing that's done in radars. So, I've talked a little bit, I highlighted a couple applications. There are many more that have been considered over time. Some of these are similar to what we've just shown. For instance, traffic monitoring is essentially a static version of automotive radar. Robotics are a combination of basically people counting, where you're trying to detect things in an indoor environment, as well as automotive, where you're trying to move around. You mentioned gesture. There's also things that are using radar to do life form detection, which fine motion. This is the child presence detection in a car, or what I like to call the ultimate baby monitor, which is detecting the breathing of your baby sitting in their crib when you can't. The radar program started when my first child was born. And you have those baby monitors and they're totally useless. Like the first night that he slept all the way through the night, I was terrified because I assumed he died. And of course he survived, which I'm very thankful for. But, if you're just looking at a video or you're just listening to their breathing, you're just listening to sounds, you get really no indication. Radar, every time they breathe, their chest moves by 0.5 millimeter, 1.5 millimeters. You can detect that with a radar sensor. So in conclusion, millimeter wave radars, these sensors offer a ton of velocity and distance information. They're considered to be good for, their strengths are they preserve privacy. Unlike a camera sitting in an indoor environment, radars really can't tell much about a person. They operate well in occluded environments, but because of the limited information, particularly angle information, you really need to have a lot of high-level signal processing to extract information out of this, and a lot of knowledge of the application and the scene that you're looking at. The biggest challenge that I'll highlight here is still, can we improve on the angular resolution to be able to handle static scene processing? I think this is one of the toughest challenges, an area of active research. And then, we look at new applications. It's great to have a lot of new applications that are proposed, but really need to be cognizant about sort of what are the strengths as what are the limitations of radar. So radar can't solve every problem, but I think it can solve more problems than it's doing today. And with that, I'll conclude the talk and open it up for discussion.